Thank you, Danielle, and good afternoon to everyone. Today's topic is on the seismic method, and this is more of a geophysics basic lecture, and I suspect it would take about 30 minutes, maybe a little less, so that will leave plenty of time for questions should you have any. On the front slide here, we have a seismic acquisition boat. We have a very classic seismic line, first published in 1977 in Memoir 26 from offshore West Africa. We have a piece of seismic in the background, and then the color is a horizon that has been mapped, and you can see 2, maybe 3 faults in there. This is another view of a mapped horizon that has a series of faults. We'll eventually get to an exercise related to this particular data set. And here's an image of a visualization center where we have a presenter, we have a number of wells, which are the vertical red lines, and we have pieces of seismic in the background there and some cubes here. And then the color would be a horizon, perhaps to the top of a reservoir. So in exploration, at least, the basic workflow would be to identify opportunities. Where might some blocks be available that have high potential for oil and gas? We have to capture those areas through a lease sale. We acquire seismic data. We would have preliminary, probably sparse seismic to identify the opportunity and capture the area. Once my company bids and is successful on, let's say, 3 blocks, we might then acquire a denser seismic grid or even a 3D seismic survey. The seismic data has to be processed. Then we have to have someone interpret that data, and that's mostly what I've done through my almost 40 years. We would identify areas of interest where we think we might have hydrocarbons. That would be a prospect. We do at least first pass economic analysis. Is there enough hydrocarbon potentially there that we could make money? We present that to management, and we do such a great job. They say, yes, let's drill a wildcat. And we drill the wildcat, and if we don't find what we thought we would, or we don't have enough volume of hydrocarbons, then we're going to drop the prospect. But we don't like to think about our failures. Let's think more positively. We discover hydrocarbons. We might have to drill 1 or 2 or 3 confirmation wells. We can prove to management that, yes, it is an economic quantity of oil and gas. We can make a profit off of that. And then the explorationists would turn it over either to development geoscientists or production geoscientists. And as we go through the series of lessons, and if you do the exercises associated with each lesson, you'll be going through this particular workflow. So the seismic method, we have to get images of the subsurface, and we use acoustic energy. So I have an energy source labeled over here. And along the surface, we're going to have listening devices. Those would be geophones in land operations or hydrophones in marine operation. So we'll have our energy source go off. Let's say it's a stick of dynamite, not used all that much anymore, but in the 30s and 40s and 50s, dynamite was the main energy source. So we have a little counter here. So the explosion goes off, bam, 0.1 seconds, 0.2 seconds. The energy hits boundary. Some of the energy is reflected up, and it's detected at the first listening device at 0.4 seconds. Most of the energy is transmitted down. Let me start that animation again. So 0.1, 0.2, some energy is reflected. Most of it's transmitted, 3, 4, 5, 0.6, 0.7, and the second listening device receives reflected energy off of the deeper interface at 0.8 seconds. So if we were to look at the output for device 1 and device 2, the listening devices, the first device sees energy reflected from the first interface, and that starts at 0.4 seconds. The second device sees energy reflected from the deeper interface, and that reflected energy starts at 0.8 seconds. So we can use this basic concept to collect data either in a land environment or a marine environment. And what we'll use is we'll use thousands of explosions or vibration points or air gun pops, and we'll probably have 1 million receivers, and we're going to arrange where the shots are located and where the receivers are located in some organized fashion on the surface of the land or the surface of the sea. And by doing that, we can collect the raw data that through seismic data processing, we can get images of the subsurface. So we have 2D seismic grids, sparsely spaced lines, and then we have 3D seismic surveys. And 3D surveys is the preferred type of seismic data to get. I would say probably 80%, maybe a little bit higher, of seismic that's collected these days would be 3D seismic, and maybe 15–20% is still 2D seismic. We have to plan how to acquire the data. First thing we need to look at are the imaging objectives. What subsurface area do I want to illuminate with the seismic data? What is the depth of the target, or we may have several targets? What sort of structural dips do we expect in the area? What sort of velocities or velocity structure? And then what's the size and the thickness of the bodies? So maybe we are exploring for fluvial channel sands. And so are those sand bodies 1 kilometer wide and 500 meters thick, or are they wider or narrower? Are they thicker or thinner? Those imaging objectives control what the survey parameters are. So we need to know what the surface area is in order to get the image area at depth. We need to know what sort of fold and offsets and sampling and what the shooting direction will be. We'll have a lesson on seismic acquisition, and I'll go into more detail on the area and what fold means and what offset means, and how shooting direction plays a part. The main thing in seismic acquisition is we have to attain a proper balance. We want the right data quality so we can answer the business questions, but we unfortunately have limited budgets, and so we don't want to overspend and get much higher quality data than we actually need to answer the business objectives. This is always tricky because we might collect the survey in the exploration phase where the requirements are not quite as stringent, but if we make a discovery and we start to develop a field, the business questions change, we need more detail, and then find out that we saved a little bit of money in exploration when we acquired the seismic data, but now we wish we had spent some more so that we have the better data quality as we go into development and production. This image shows some vibrator trucks. So we have 1, 2, 3, 4 vibrators, and they have metal plates that are pressed down to the ground, and through electronics we're able to vibrate those plates and send energy down into the subsurface. So we don't use a single vibrator truck, but we use a series of them, and there's a lot of physics or geophysics involved in how best to operate a team of trucks so that we get the best amount of energy going down and the best seismic images of the subsurface. This is a picture of a marine operation. We have one boat, and it is towing a lot of equipment. There's some white in the water here, and there's some white in the water here. These are 2 air gun arrays. Looks like this one just fired. There's more white there. This one fired previously. maybe a few seconds earlier. And then there's white here with a trace in the water column, white here with a trace, white here with a trace, white here with a trace. These are the receivers, the listening devices, the hydrophone cables. And so this boat has two source arrays, A and B, and it has 4 receiver streamers. And so every time the boat sails over an area, it is collecting 8 lines of subsurface data. These streamers can be on the order of 4 or 5 or 6 or 7 or up to 10 or 12 kilometers in length. So a lot of equipment to keep track of, a lot of effort to figure out how to properly arrange everything so that we get the right data quality in our area of interest. This slide shows a field record. This is data that is collected. This is a marine case. It's on the axis here, we go from close to the boat to far from the boat. In this case, it's a 6-kilometer long cable. And these black and white streaks that are hyperbolic in shape are the seismic reflections that we are interested in. So this is the raw data collected in the field. It is not processed at all. And the reason why it's hyperbolic in shape, this is marine, so it looks like 600 milliseconds or 0.6 seconds two-way travel time is the water depth. I happen to know the velocity of seawater is 5,000 feet per second or 1,500 meters per second, and so I can calculate quite easily what the water depth is. For the shot to receiver near the boat, the energy goes down almost purely vertical, bounces and comes back up. That's a shorter path than energy going out to a receiver, let's say 5 out of the 6 kilometers. That energy has to go down and come back up. It has about the same vertical component, but it has a much longer in distance lateral component. And so it takes a longer period of time for energy to travel the blue path than it does down and up for the red path. And that's why near the boat, the times are shorter. Further and further and further away from the boat, the time for each of the reflectors, such as the seafloor, gets longer and longer. In the lesson on seismic data processing, we'll talk about how we understand this curvature as a function of distance behind the boat, and we can use that to correct the data so that we can take out all of that curvature. So we collect the seismic data. Here's a field record in a marine survey. We send that to our seismic data processing people. They have lots of tools in their toolkit to try to improve the image that the interpreter is going to get, and they generate seismic data. This is an example of a 2D line out of a 3D volume showing the layering within the subsurface at this particular location. The magenta line there is a fault that I've interpreted, and then the blue and the red, orange reflection bands, peaks and troughs, is telling me something about how the rocks are layered or what the strategic is. And we'll talk a lot about getting structural information out of seismic and stratigraphic information out of seismic as the series of lectures continue. So here we have a little diagram. Here's my acquisition boat. Here's the air gun array. So bam, energy goes down, hits the interface number 3, comes up into receiver 1. The energy could also go down, hit, and be detected at receiver 2, receiver 3, receiver 4, receiver 5 as shown. So there is a direct arrival that from the air gun goes directly to the water column to receiver 1, to receiver 2, 3, 4, and 5. That's the direct arrival. And if I plot receiver number, which is also equivalent to distance behind the boat, versus two-way time for the energy to reach the receiver, the direct arrival forms a straight line, and the slope of this line will tell me what the water velocity is. And it would be pretty close to 5,000 feet per second or 1,500 meters per second. It does vary a bit with water temperature and salinity. For the blue pass, the reflection off of the interface between the white and gray layers, I've displayed the energy that would be detected from those reflection points or bounce points. And as I mentioned earlier with the shot record, they are hyperbolic in shape, curving down as we go further and further from the boat or the source array. One of the things that the seismic data processors will do, they will resort the data so that if I am interested in the geology at this interface within the red box A, the seismic data processors will go through and figure out which shot into which receiver had a bounce point or a reflection point there. And since the angle of incidence is equal to the angle of reflection, if the layer is horizontal or nearly horizontal, that bounce point is halfway between source 1 into receiver 1, halfway between source 2 into receiver 2, and halfway between source 3 and receiver 3. So we call this a common midpoint, go through all of the raw data and find shots and receivers so that the midpoint would be along this red line, including the little red box. So we get what are called CMPs, or common midpoints. And so this is a common midpoint gather, so a collection of the shot receiver pairs associated with the red box A. And again, we see that everything is hyperbolic because the time for shot 1 into receiver 1 will be less than shot 5 into receiver 5, again, because the component of lateral distance increases as the offset angle increases. So we have a CMP gather. We can measure what the curvature is for a particular reflection. Here is a peak marked with the blue line. From that curvature, we can calculate what the average velocity is down to that particular depth of that reflector. And so one of the things that the seismic data processors will do after they've collected these common midpoint gathers, they'll analyze the curvature of those hyperbola, and that will give them a way in which to get an approximation of what the velocity structure is at any particular point within the survey area. We know the physics involved. We know why the curvature occurs. If we have an idea or a reasonable good estimate of what the velocity is, we can take out that delay because of offset, and so we can re-datum these blue reflections, these peaks, so that they are flat-lined. And so it would be as if each of these shot receiver pairs was not at some given offset, but what we're trying to represent is what would the data look like if each shot and receiver had no distance in between them, what we call zero offset. If the velocity that we use is correct, everything will flatten. If, however, the velocity is a little too slow, we don't correct it enough, and so we'll still have some curvature down. If a velocity that we use is a little too fast, we'll overcorrect, and so the reflection as a function of offset will curve slightly up. So we use this to try different velocities for different reflectors at different depths, and when we get all of the peaks or all of the troughs aligned, we say we have flattened the gather, and that tells us that we have a pretty good estimate of what the average velocity is. And so we will do a velocity analysis and thereby get information about the velocity structure throughout the survey area. So we have a CMP gather. We'll flatten that gather. Let's say we have 10 shot receiver pairs in this gather. We have 10 traces that would all be from a common midpoint. And then what we'll do is we'll sum all 10 of these and get a single trace at the location of the midpoint. And if we have 10 traces that we're adding together or summing, we say that's 10-fold data. If we had 12 traces, it would be 12-fold. If we had 6 traces, it would be 6-fold. So fold is a code name for the seismic processors. It's really how many traces have we added together. The reason we add these traces together is because we are listening for very faint energy, acoustic energy from these reflections. And so anything that is generating noise, like the boat itself or the waves or storms or other types of noise in the area, we can cancel that, because if the noise is truly random on each of these traces, the reflection information about the geology is constant, but the noise from the boat and the waves and wind will all tend to cancel out. So by stacking multiple traces with different shot receiver offsets, that greatly improves the signal to noise ratio of our data. We do have a positioning problem. I've been talking about flat layers. What if our interface is dipping or sloping or inclined? The energy source is up here. The energy will travel down, hit this surface at 90 degrees, bounce and come back up. This is for our zero offset. We have our receiver at the same location. And so the receiver listening here realizes it takes 0.2 seconds to go down, it takes 0.2 seconds to come up. It will plot the information right where the shot receiver is, or the common midpoint is, and it'll put it at 0.4 seconds. So instead of placing it here, it's going to place it here. And so there's an arc that we can draw from where the reflected energy actually came from to where it's displayed on the seismic. And again, if we understand the physics, there are ways for us to compensate and correct the reflected energy so that we can move it back, or the processing term is we can migrate the reflections back to close to where the true reflection points are in the subsurface in the presence of dipping surfaces. So that's a little bit about the acquisition and the processing. The next step is to do seismic interpretation. I mentioned this is a classic line. We have an exercise later on in the course where you can work some interpretation on this. We can derive the local geology from the subsurface images. We can map faults and other structural features. We can map unconformities and other major stratal surfaces. We can interpret depositional environments. We can infer lithophases from reflection patterns and also from the velocities that our seismic data processors generate for us. We can predict ages of some of the stratal units, and then we can examine elements of the hydrocarbon system. Well, what are these elements, Fred? Well, that was our topic in, I think it was lesson 2. That's the source, reservoir, trap, seal, and migration. So there are 3 exercises associated with lesson 5. One is to calculate, given an inclined reflector, where the actual seismic event would show up on a 2D seismic line. And as a little hint to how we would do that, if we have a shot and receiver here, so we're going to assume 0 offset, the energy would go down, hit this at 90 degrees, bounce and come back up. we can use a compass to control that, that distance on the diagram. And then where would it be positioned? It would be positioned under the shot receiver pair at location 1 at the same time. And so we can swing an arc until we're vertically underneath the location. You can do the same thing with position 2 and swing an arc, 3, 4, and 5, and you'll get red dots using my coloring here, and here, and here, and here, and here. So the reflection occurs a little shallower and a little down dip from where the actual interface is. And so that's the goal of exercise 1, to understand what happens when the interfacers have some dip on them. The second exercise, we have an anticline shown here. Again, we're going to assume 0 offset, shot and receiver in the same location, and you'll be asked to consider the reflection at position 1, 2, 3, 4, 5, 6, 7, and 8. 1 and 8 is pretty simple. It goes straight down and straight up, but the other ones have non-vertical ray paths, and so you'd have to use the compass again to swing out arcs to figure out what would it look like on a 2D seismic line before we do any correction for dipping reflectors. And exercise 5C, instead of an anticline, we have a syncline. And again, you would determine, given this geometry and these shot receiver pairs at positions 1 through 8, what would it look like on a 2D seismic line before we correct for mispositioning. So that covers our topic, seismic data, very general. Our next session will be on July 11th. No sessions next week or the following week, which is the week with the 4th of July holiday. So on the 11th, we'll talk about seismic reflections. Then we'll get back into a little bit more geology. We'll talk about some of the elements, source, reservoir, structure and traps, seal and migration. And then as we get into August, we'll talk about seismic interpretation and various other topics. So lesson 16 is the one that I referenced to on seismic acquisition. 17 is on seismic processing. And then we talk about seismic interpretation, and we'll talk about seismic sequence analysis, seismic facies. We'll talk about seismic attributes, et cetera, et cetera, et cetera. Talking about how to estimate reserves in a particular field, and what the development geology and geophysics people do, what production geology and geophysics people do. So I'll turn it back over to Danielle, and we'll have plenty of time for questions either on the topics from today or topics from previous presentations.
Great, thank you, Fred. So I'll give everyone a minute if they want to write in their questions in the question box. Just give it a second, see if there's any that pop up.
I suspect we have a largely geophysical audience with the iris connection, and nothing I said would place fear or trepidation in the geophysicist's heart enough to ask a question.
Yeah. Okay. Well, I don't see any questions, Fred. So I guess with that, it's a short session today. Like Fred said, we're going to skip 2 weeks, and then we'll do lesson 6 on July 11th. So stay tuned for that. And if people are having trouble finding where they can get the registration information, I would suggest going to the IRIS mailing center. the message center and subscribing to our webinar list. So I can include that information in the YouTube email and survey email today. Well, great. Well, thank you, Fred, so much for doing this lecture, and we'll see you on the 11th.
Okay, thank you everyone for tuning in.
All right, great. Thanks. All right, bye, everyone.
Goodbye.